We're going to continue with chemical equilibrium today. And again, this all fits into big idea 6. And today, more than ever, you will see the effect of external perturbations on chemical equilibrium with Le Chatelier's principle. We're going to talk a little bit more about equilibrium setup. And from your do now activity, again, you should be able to write Kc expressions, solve for concentration when given other concentrations in Kc. And today we're going to introduce the concept known as Kp, written here. Come back to that in a minute. So when you write a Kp expression, again, as you already stated, products on top, reactants on bottom. Partial pressure of reactant G raised to its coefficient. Partial pressure, that's not a reactant. What is that? A product, because products go on top. So partial pressure of product G raised to its stoichiometric coefficient. Partial pressure of product H raised to its stoichiometric coefficient. Reactants on the bottom. So again, the only difference here is you have partial pressure as opposed to concentration that you had here. Also with KCs, you're going to have gases and aqueous. KP's gases only. You never, ever, ever include solids or liquids in equilibrium constant expressions. You can convert between Kc and Kp. This is not something that they're going to ask you. They no longer give you this equation, so we won't cover it. And again, as we already mentioned, we don't include solids or liquids in equilibrium constant expressions, and that's because their concentrations don't change. So no solids, no liquids. If you consider decomp of calcium carbonate, again, you're generating simpler substances. They have to be elements or compounds from one reactant. Your Kc is equal only to the concentration of carbon dioxide. Why did we not include calcium carbonate or calcium oxide? Because they're solids. Kp would just be the partial pressure of CO2. So let's take a look at the following problem. We'll example it off. It says the reaction of steam with iron is an old method of producing hydrogen gas. Write the equilibrium constant expressions Kc and Kp for the reaction shown. So what would be our Kc? What goes in the numerator? Go ahead, Faith.
Fe3O4.
Why would you not include that?
I'm just kidding, it's a solid.
Right.
Okay, so it's just H2 to the 4th. The concentration, yeah, that.
Where'd the 4 come from?
The coefficient.
Should I put the 4 in here too?
No.
No, 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 no. What goes in the denominator?
H2O to the 4th.
You got it.
And then you can cancel the 4s. No?
Because those not necessarily the same quantity, right? Kp, partial pressure of hydrogen gas raised to the 4th. Partial pressure of water raised to the 4th.
Can't you still cancel them? Because if you, like, 4th root the whole thing, they'll both go away. So you can just cancel.
But if you consider, let's say for example,
If that's a 2 to the
Right.
4th is 16.
but no, and if it's a 1, so if you have 2 to the 4th over 1 to the 4th, that's 16. But if you did this, that would be 2. So the answer is no.
Okay, my bad.
If these quantities were the same, then yeah.
Oh.
Alrighty. There are 2 additional problems in your textbook we're going to take a look at. On page 631, and this is where you'll find all the homework that I'm sure you are actively involved with. 631, number 26. I'll blow this up on the screen so you can see it. Give it a shot. Let's make sure you are comfortable with this type of analysis. And you will see the importance of working through homework problems. Here's 26. At high temps, elemental nitrogen and oxygen react to generate nitrogen monoxide. Suppose the system is analyzed at a particular temperature and the equilibrium concentrations are found to be nitrogen gas 0.041 molar, oxygen gas 0.0078 molar, and nitrogen monoxide 4.7 times 10 to the negative 4 molar. You want to calculate the value of K. Give it a shot. Should be pretty straightforward. I can't see that. Did you get the information down? Yes? What'd you get? What'd you get?
6.9 times 10 to the negative 4.
I got 1.4.
You didn't square the top.
Correct.
Jeez.
He's right. Little direct. All right. Don't be peeking at that one yet. I'll make that little.
There's no units for
There are no units for KC because they are equation dependent, and so chemists just do not use units for Ks.
All case?
All Ks. They are going to be unitless. Alrighty. Yes, yes? No probs? And I can't emphasize enough the importance of practice problems. That is the struggle. If you don't practice before the quiz, when it gets to the quiz, it's just a mess. Let's take a look at 44. I'll blow it up. Yes, yes? 44. Here they're giving you the KP. They're giving you partial pressures, and they want the partial pressure of nitrogen monoxide at equilibrium. And again, if this is a part 1 question, these numbers will be very simple to divide. What'd you get? What'd you get? All right. Easy does it.
Chase.
Stop.
Wait, how do you didn't square something. No,
Don't look up till you have it done. If you didn't get it correct, look at my setup, see if you have the same setup. Is it a setup issue or is it a calculation issue? Yep. Did you not get a concentration?
I didn't see the 109.
The 109 was the KP that was provided. It said it has a KP of 109, so that was given. And then I just interchanged these,
Okay.
and then I had to take the square root because of this.
It's on the 100.
This is extremely low level chemical equilibrium. You must have mastery of this concept before Friday's lesson, because that will take it to a whole nother stratosphere. Okay. We want to examine when equilibrium constants are actually utilized, and we will link it back to thermodynamics. When you have huge KCs and KPs, 1 times 10 to the 10th and greater power, like 10 to the 10th, 10 to the 11th, 12th, 13th, 14th, etc., that means that the reaction essentially goes to completion. You're not looking at a reversible reaction anymore. You're only looking at a reaction that goes in the forward direction. It is thermodynamically favorable. For example, if you look at the synthesis of water, this is not really an equilibrium type reaction. It really should just have a forward arrow because the KP is ginormous. A very small value of Kc or Kp signifies that the forward reaction as written does not occur to any significant extent. You're going to see a double-digit negative power, something times 10 to the negative 10, negative 11, negative 12, negative whatever. For example, calcium carbonate does not decompose at 25 degrees Celsius. If it did, many of our statues would be crumbling from the weather alone. Okay? Keep in mind that 25 degrees Celsius is ever so slightly higher than room temperature. Outdoors is even hotter, especially for those of us who live in sunny Florida, and you don't want those statues coming down.
And coral.
Anything along those lines, exactly. So equilibrium constants are for reversible reactions that are at equilibrium. Don't confuse this with kinetics. Kinetics tells you how long it takes to reach equilibrium, how fast the reaction occurs. Chemical equilibrium is when the rate of the forward and reverse reactions are equal. The other thing I want to mention, because I'm seeing a lot of this on quizzes, semester exams, etc. If you have a Kc greater than 1, the forward reaction is favored, and delta G will be negative, a thermodynamically favorable reaction. When you have a Kc equal to 1, you are at equilibrium, and delta G will be equal to 0. If you have a Kc less than 1, the reverse reaction is favored, and delta G will be positive, a thermodynamically unfavorable reaction. In the previous chapter, we talked about enthalpy and entropy in regard to thermodynamic favorability. You have got to be able to make connections between chapters. When you take your AP exam, we've already talked about the fact that on part 2, questions 1 through 3 are the longies worth 10 points each. They will not just assess chemical equilibrium. You can mix chemical equilibrium with thermodynamics. You can link it to kinetics. You can link it to stoichiometry. You will see numerous concepts assessed on each question. It's very important that you make these critical linkages at this point. You should be comfortable with the concepts, and now we've got to integrate them. If you haven't mastered previous ones, the integration becomes a big issue. But you will see in this chapter a link back to thermodynamics, and it is expected that you can go in that direction, and we'll get you there. We said previously that equilibrium constants, KCs or KPs, are for equilibrium conditions. So for example here, if you were writing a KC expression, these concentrations represent equilibrium concentrations. We don't write equilibrium there because we know KC means that you are at chemical equilibrium. Same thing with KP. These are the partial pressures when equilibrium has been reached. We said equilibrium is reached when the rate of the forward and reverse reactions are equal. And graphically, we saw that last time because you saw the plateaus on the graphs. So you know the concentrations or pressures at equilibrium because that's where the graphs will plateau, straight lines. We want to introduce a concept here that we will come back to in great detail next time, but we'll introduce it here. The reaction quotient helps you predict whether the forward or reverse reaction is favored and why. The reaction quotient Q looks just like a KC or KP, but you have non-equilibrium conditions, typically initial conditions, non-equilibrium conditions. Q's are not constants. They will change, where KC's are constants unless the temperature changes. Q's allow you to predict whether the forward or reverse reaction is favored, and the way you determine that is by calculating it Q and comparing it either to a given KC or a calculated KC. Q's are written just like KC's with one change. So in the do now problem we looked at initially, if you were going to write the Q, the reaction quotient, you would use the concentration of products in the numerator and reactant in the denominator. The only difference is that these are non-equilibrium conditions, typically initial. I'm putting an I there where I equals initial or non-equilibrium. You can calculate Q from initial concentrations or non-equilibrium concentrations, and you can compare it to K to determine if the forward or reverse reaction is favored. If your Q is less than your K, the forward reaction is favored, because the forward reaction will drive these concentrations up and this down so that you can get to equilibrium where Q and KC are equal. If Q is greater than KC, then the reverse reaction is favored to drive these concentrations down and this up so that you can set these two equal to one another at equilibrium. And that is what is listed here. If QC is less than KC, the net reaction proceeds in the forward direction. By driving it in the forward direction, you will generate more product, increasing your Q to match your KC. If QC is greater with the R, the net reaction proceeds in the reverse direction, decreasing product, increasing reactant, so that you can elevate this to match this. When they are equal, you are at equilibrium. In the following example here, it says, in which direction would a net reaction occur if the conditions for the reaction below were initially hydrogen iodide at 1 molar and initial hydrogen and iodine concentrations at 0.1 molar. Whenever you see a problem that says in which direction, you're looking to calculate Q and compare it to Kc. If it's less than, the forward reaction is favored. If it's greater than, the reverse reaction is favored. In this particular example, all of this is given. I'm going to calculate my Q. 0.1 squared over 1 is 0.01. Q is less than Kc, and so the forward reaction is favored. That will drive up the concentration of product so that you can achieve equilibrium where Q and Kc are equal. We'll see a lot more of this next time. At this point, just understand the conditions and what happens, but we'll drive that point home in great detail next time. Our focus today is going to be on Le Chatelier's principle. Some of you have seen it before, and I think you will recall it. There are a few new aspects, but not a lot. For some of you, this will be brand new. If you read it in a textbook, I think it would be very confusing to you. I'm going to explain it very simply. We're going to do a whole bunch of examples, and before you walk out today, I think you'll feel very comfortable with Le Chatelier's principle. For those of you with great familiarity with it, focus, master the old concepts, and really take a look at the new ones. Before I get into it, in terms of what's in your notes, I'm going to start it very simply to give you a good springboard. Le Chatelier's principle says that when you change or stress a system that is at equilibrium, the system will react in such a way to at least partially undo the stress you have imposed. Those stresses or changes include changes in concentration, temperature, pressure, or volume. For example, let's say that you have some generic equation and if I put the energy term here, is the reaction endo or exothermic? Exo, and I could have given you some delta H value. It would be
-3. Wow.
negative, indicative of an exothermic reaction. You already know how to write KEQ expressions. What we want to look at here is what happens to this equilibrium system when we apply a stress, whether it be temperature, pressure, volume, concentration. Whenever you increase concentration or temperature, equilibrium will shift away from that entity. If you decrease concentration or temperature, equilibrium will shift toward that entity. And I'll explain all of it. When equilibrium shifts in the forward direction, what happens to reactant concentration? It decreases because you're shifting away from it, so they get used. And what happens to product concentration? When equilibrium shifts in the reverse direction, now reactant concentration increases and product concentration decreases as those products get consumed, acting as reactants. When you increase pressure or decrease volume, equilibrium will shift toward the side of the reaction with fewer volume units of gas. And that's due to Boyle's law, that pressure and volume are inversely related. If you decrease pressure or increase volume, equilibrium will shift toward the side of the reaction with greater volume units of gas, also because of Boyle's law.
Dr. Bailey?
Yep.
Let's say like you have, like you're doing volume, and you have like the reactants have 50 milliliters
Of gas?
of gas, yeah, and the products have like 10. Then you increase the volume on the product side by 10. Would anything happen?
You don't increase one side or the other, you increase the volume of the system as a whole. So if you increase the volume, equilibrium will shift to the side of the reaction that has more volume units.
So go back.
That's the coefficients, right?
Mm-hmm.
What does it say after what? Greater.
Greater.
But
It looks like quarter.
Oh.
wait, but then why would that happen? Like I remember the rules, but I don't remember why.
Okay, and we're going to get into that, and we actually just did pressure last year, not volume, and that may be why it's not clear to you. We're going to do all of it, I promise. Seatbelt on. It's not going to be bumpy. I promise. Here's your setup. Let's say, for example, that I increase the concentration of A. In which direction will equilibrium shift?
Away from
How would we know?
All right. Don't write away or toward. You have to say right or left or arrows.
We don't. Oh,
If we increase A,
Oh.
we need to shift away from A. So equilibrium shifts in the forward direction to use the added A.
We can write forward, right?
Forward would be better. let's look at what happens to the substances. Initially, we added A, but with the forward shift, A will decrease, B will decrease, but what happens to C and D? They increase. Whatever you point toward will increase in amount because that gets generated. Let's say, for example, that we decrease B. All right, and you have that equation in front of you.
Is the second arrow in A supposed to be smaller?
Yes, it doesn't decrease as much. You only partially undo the perturbation. If you decrease B, equilibrium shifts in the reverse direction to replace lost B. And now let's look at what happens as well. Initially, we decreased B. With the reverse shift, what happens to reactant concentration? They're going to go up, and C and D will go down because they get utilized. In the equation shown above, let's say that we increase temperature. Looking at that equation, and again, it's easier to keep working it, write on it with pencil. If we increase temperature, equilibrium will shift to the left to use the heat added. When you increase, you shift away from that entity. So in this exothermic reaction, when you increase temperature, equilibrium shifts to the left to use the heat added. When you shift to the left, what happens to the concentration of reactant? And the products go? And you will note you don't have up and down arrows here. How come?
Because you're not increasing concentration, just temperature.
Exactly. We'll do the pressure piece when we get there. That's the beginning.
Is it possible to increase temperature on one thing or a specific like part of it? You increase temperature on A but not B?
No, you increase temperature of the system. You have a reaction that's equilibrium and you heat the whole thing. You're not just zipping each little one in terms of temperature or pressure. You can increase, if you want to increase the concentration of something, you're going to throw more of it in. So there you can get specific. But with temperature and pressure, it's just going to be the whole system. Good question.
That's okay.
Yep.
You know how in the lab we just did, we started with water that was like heated ahead of time? If you start with one of your reactants at a different temperature, will it affect the overall, like, where the heat goes in that equation?
No, because when you're doing these types of reactions, before you stress them out, they're already at equilibrium, so it will be at a constant temperature.
Okay.
That's a good question, too. All right, we're going to go through each type of perturbation, many examples. Go ahead, Sam.
So when you decrease the temperature, what would be like the explanation?
If you decrease temperature here,
It would shift to the right, but like
correct.
be the explanation.
Okay, so if you decrease temperature, equilibrium will shift to the right to replace the heat lost.
Okay. Makes sense.
And we'll work on those explanations here. We'll write them out. All right, in regard to concentration, this is the fancy schmancy way. It is all written out. We've been through this. If you increase reactant concentration, equilibrium shifts to the right, and that's to utilize that particular reactant that you added. With a forward shift, reactant concentrations will decrease, product concentrations will increase. If they ask you what increases, just indicate the product will. Don't go after the one that goes down and up and up and down. That sometimes can be confusing unless you have no choice. If you increase product, equilibrium shifts to the left, increasing reactant concentration, decreasing product. Be careful. Changes in solid or liquid concentrations don't affect equilibrium. They're not included in KC expressions. And they'll go for that on a part 1 or part 2 question. If they ask you about, in which direction will equilibrium shift when more solid is added, no effect on equilibrium. All right? Ignore the solids, ignore the liquids.
That are more likely to get a multiple choice though, right?
You betcha. First example shown, ammonia and oxygen gas making nitrogen monoxide and water vapor, all gases. You've got a delta H of negative 6.2 kilojoules. Is that endo or exo? Exo. So the energy term would go right here. And at your level, you may want to add in plus E, because that will help you focus on a temperature-based question. First one says, if ammonia concentration is decreased, equilibrium will shift to the reverse or left to replace the ammonia lost. If oxygen concentration is decreased, equilibrium will shift to the left to replace the O2 lost.
Should we say, we have to write it out, should we say about O2 lost and not perturbation?
Nah, keep it simple. All right. If NO is increased, equilibrium will shift to the,
Left.
you're increasing here, which is on the right side, you shift away, so equilibrium shifts to the left to use the NO added.
Could you say to use up the excess and that be the explanation?
Probably. Here's the AP level question. What types of perturbations would result in an increase in nitrogen monoxide? And your approach. If you want to increase nitrogen monoxide, in which direction do you want equilibrium to shift? Forward. So what would cause a forward shift in equilibrium? An increase in
Concentration of the reactant.
concentration of either reactant,
Decrease in H2O.
a decrease in water, or a decrease in temperature. So that's where the AP level question comes in, not just bare bones, which way do you go? What types of perturbations would result in?
Decrease in temperature will increase concentration.
Yes, because if you decrease temperature, in which direction will equilibrium shift? Forward. And if you shift forward, reactant concentration goes down and product concentration goes up. And so you will get an increase in nitrogen monoxide.
Would that be like a select all that apply, multiple choice?
It could be, or it could even be a part 2.
Really?
You don't get too many select all that apply at the AP level. I know you see it all over the FSA, but believe it or not, AP, we're not seeing that very much. What you're very often going to see on the AP exam is, keep in mind, its choices A through D. So that has been simplified. It used to be A through E. Very often you can get it down to 2, just like on your quizzes, and then you're like, ooh, which one is it? So that's what we're seeing a lot of. But that would be maybe more of a part 2, design an experiment in which you would get an increase in nitrogen monoxide concentration, and you could indicate that, you know, when the system's at equilibrium, more ammonia would be added to the system, resulting in a forward equilibrium shift. Thus, more nitrogen monoxide would be generated.
That would be a short.
Very shorty. All right? The second equation shown is similar to a lab that many of you did. I throw this equation up here because not only does it look strange, you have complex ions, but in the lab that we're going to do next week, you also will see an equilibrium reaction involving complex ions. So I just wanted you to see it here so it wasn't so shocking next week. It's a reaction we're going to be carrying out twice, not only for Le Chatelier's principle illustration in the lab, but also for KC determination using spectrophotometers later this 9 weeks. For those of you who ran this reaction previously, this substance is blue, this substance is pink. So this is a great illustration of Le Chatelier's principle because it typically is going to be a qualitative assay. You start with a blue substance, you cool it off, you get a pink substance. You throw acid in, and you get a blue substance. And what do pink and blue make when mixed together? Purple. So at equilibrium, it's purple. And so it really works well.
You demonstrated that, right?
On, like, the first day-
Actually, in terms of the lab we did last year, if you're
No,
thinking
the first
about
day of
that,
school.
I did a demo of it this year,
Yeah,
first
you
day?
did. It wasn't in the first day of school, but it was before we did our titration lab.
Okay, so it's something in the lab last year. You would have done the concentration aspect. I demoed the temperature piece as part of your lab last year. But it is a lab. I actually love this lab, and sometimes I think it would be good to integrate it into AP, but since some of you did it, there's a secondary lab that works equally as well, and it's a lot of fun. So we're going to do that this year. But in any event, if you decrease the concentration of this complex ion, you decrease, do you move away or back toward it? Toward it. And I'll avoid the word back. I know sometimes that's confusing. So you move toward it. So equilibrium shifts to the left to replace that complex ion specifically that was removed. The naming of complex ions is really tricky. I don't want to name them for you. It's above the scope.
Can we just say complex ion?
Well, I think I would have rewritten this because you've got 2 there, so you have to be specific as to which one it is. If chloride ion is decreased, equilibrium shifts to the right to replace the chloride ion lost. The next 2 questions are very tricky. I'll hit that in a minute. If you increase temperature, equilibrium shifts to the left, correct. These 2 questions are tricky, but they're both doable at your level. If you look at this equation, I'm going to rewrite it here so that you can clearly see what is happening. Keep in mind, ions are aqueous. The water actually is a liquid. Would that be included in the KC expression? No.
When you see an ion by itself, it's usually aqueous.
All ions are aqueous, dissolved in water. Okay, so here's your equation. And this is very tricky. If you add hydrochloric acid to the system, is hydrochloric acid a strong acid? Yes, it is. So it ionizes completely. By adding hydrochloric acid, what are you effectively increasing the concentration of? Chloride ion. If you increase the concentration of chloride ion, equilibrium shifts to the left to utilize the chloride ion added from hydrochloric acid. So that is tricky.
Did the hydrogen affect
In this equation, no, but it can. And that's an excellent question as well. Let's say, for example, that we had aluminum hydroxide, which is barely soluble. So equilibrium is going to be far to the left. But you'll get a smidgy of this.
But how would we know that ionizes? Because it's not a strong base.
Correct.
So how would we know?
I understand. You are correct. It is not a strong base, and it barely ionizes at all. After the acid-base chapter, we'll be doing solubility equilibria, where this will come to play, and you'll be able to do this. In addition, if a question such as the one I'm going to pose were asked right now, you would be given the balanced equation, an equilibrium type system. Let's say that you added nitric acid. Is nitric acid a strong acid? Yes, so it ionizes completely. Are all nitrate containing compounds water soluble?
Yes.
Yes. So this would not form a precipitate. It's essentially still just aluminum ion and nitrate ion. However, and this is your question, what would the proton do in this particular system?
Would it cancel out the negative charge on the?
Why would it cancel it out? What does that mean?
Well, because the hydride. Is that
Hydroxide?
That's what I meant. Hydroxide ion has a negative one, and the hydride has a.
This is a proton.
Well,
Or a-
one of them has a negative one, and one of them has a positive one.
So when you mean cancel out, what do you actually form?
Water.
Yes.
Oh.
Don't be fresh. All right. So you form water. And so by adding nitric acid, what do you effectively do to this concentration? Why do you decrease the concentration of hydroxide ion when you add proton?
Because you're adding the water.
You're not adding water, but
Adding a proton which creates water.
exactly. So by adding this, you effectively increase the proton concentration. You provide an acid environment. That proton reacts with the hydroxide ion to make water, effectively decreasing concentration of hydroxide ion. In which direction will equilibrium shift if you decrease hydroxide ion concentration?
Right.
You are correct. All right? Going back to this problem here, let's say that I add silver nitrate. How do you know that silver nitrate is water soluble? All nitrate containing compounds are water soluble. So you're effectively adding this. Nitrate's not going to hook up with anything because it's always water soluble in a compound. What might the silver ion link to? Chloride ion. So these two substances react to form silver chloride, which is a white precipitate, so it's not going to ionize back to any appreciable extent. So by adding silver nitrate, what are you effectively doing to the chloride ion concentration? Decreasing it. And when you decrease chloride ion concentration, in which direction will equilibrium shift?
Right.
To the right. And you would know it, and that's the beauty of this assay, because this is pink, so you'd get a pink solution, and this one's blue. So this assay is just gorgeous because you know which way equilibrium shifted based on the color changes.
How would you know that silver would react with chloride?
And that's a tricky wick for you at this level now, because it used to be you had to know more in regard to the solubility rules. So my guess is they would have told you that you are making a white precipitate, and you knew the nitrate wasn't going to cause one, so looking at that equation, what's the only ion that silver ion could have linked to? And that's the goal right there.
How do you know it decreases the concentration?
Because if it reacts with something else to produce something that's a solid or something that doesn't ionize like liquid water, that effectively is decreasing it. It's as if somebody's in the hallway and they want to write up some newspaper article and they knock on the door, I need to see Sarah, and they pull you out, your concentration in my room's just been lowered because they pulled you out. It's the same concept. Yes, yes?
Yeah.
Thought it was a good analogy. All right. Concentration with two little twists.
Guess so.
Volume.
Remember the analogy you used last year?
I don't think I used that one.
With concentration, it was like if there's a bunch of people in the room, you want to get out, so you would leave, and then you would move over to the other room where it's emptier, and then if there's, and then I don't know about the decrease, but when you said it was increased concentration, imagine if this room was at maximum capacity, you want to leave, you want to get out.
That was my example last year?
That's pretty good.
I don't remember that.
That was your example last year. That helped.
All right. I'll remember. I better go and watch the videotape. All righty. Pressure. Very simple. You know that pressure and volume are inversely related according to Boyle's law. When you increase the partial pressure of the gases by increasing the external pressure and thereby decreasing reaction volume. When you increase pressure of a system or decrease the volume, equilibrium will shift to the side with the smaller volume of gases, which is determined by the stoichiometric coefficients. When you decrease pressure, equilibrium shifts to the side that has the larger volume of gaseous substance. If there is no change in the volume, let me rephrase. If you alter the pressure, but the volume on the left side and the right side of the equation for gases is the same, there's no effect. So that example would look something like this. If you had, let's say, hydrogen gas and iodine vapor, equilibrium to form 2 moles of hydrogen iodide gas. If you increase the pressure in this system, there's no effect on equilibrium, and that's because the volume of gaseous reactant, which is 2 mils, is the same as the volume of gaseous product, which is 2 mils.
Would it be the same if you increase volume, it would have nothing?
Exactly.
So it's only with pressure volume.
And again, it can be mils or liters. Just use the same unit when you explain. In contrast, if you have this reaction, and you increase the pressure, equilibrium shifts which way? To the right, because the volume of gaseous product, which is 2 mils, is less than the volume of gaseous reactant, which is 3 mils. And you know that pressure and volume are inversely related according to Boyle's law. Similarly, if you decrease the pressure, equilibrium shifts to the left because the volume of gaseous reactant is 3 mils, which is larger than the volume of gaseous product, which is 2 mils. There's 2 AP level pieces to Le Chatelier's principle that you'll see here. They're really very easy. It says in yellow, if an inert or noble gas such as helium, neon, argon, krypton, xenon, radon, is added at constant external pressure, the volume expands to accommodate the added gas. So if you add a noble gas at constant pressure, equilibrium shifts to the side with the larger volume of gas to accommodate the extra gas you just added. In contrast, if that noble gas is added at constant volume, no effect on equilibrium because you can't make it work, if you will, because volume is constant, so a shift is not going to assist in any regard. You usually see what's listed in number 4, not 5. Let's walk through this example here. It says, consider the reaction, and this is the one I just gave you. In which direction will a net reaction occur if additional nitrogen dioxide gas is added? Equilibrium shifts to the left to use the NO2 added. In which direction will a net reaction occur if the reaction mixture is transferred from a 1.5 to 3.5 liter flask? So what are you doing to the volume there? Increasing it. So you want equilibrium to shift to the side with the larger volume, which would be the left. So equilibrium shifts to the left because there's 3 moles of gaseous reactant in the compared to 3 moles compared to 2 moles of gaseous product. This is the one we just did. So if you increase pressure, equilibrium shifts to the right because the volume of gaseous product, which is 2 mils, is less than the volume of gaseous reactant, which is 3. In which direction will equilibrium shift if neon were added at constant external pressure? Equilibrium would shift to the it says constant external pressure. You shift to the side with the larger volume, so equilibrium would shift to the left because the volume of gaseous reactant is 3 mils, which is greater than the volume of gaseous product, which is 2 mils.
You're adding the neon to the reactant side, right?
You're throwing it in to the system. You can't add it to one side or the other. The reaction's running and you plop it in. But equilibrium will shift to the left due to the addition of that gas because the volume in reactant side is greater. So by shifting it to the left, you can accommodate that extra gas. But you don't add it to one side or the other.
Is that how they would ask you?
I think so. I think that's actually what I saw in last year, so I'll take a look.
What is it? And it would be the same exact way, like, if it was asking for constant volume mixture?
If they asked at constant volume, there'd be no effect on equilibrium. Equilibrium wouldn't shift. All right. Changing equilibrium temperature, we already said. There's one key piece I want to add here. It says the only variable or stress that affects the value of Kc is temperature. Neither concentration, pressure, nor volume affect the value of Kc. Only temperature affects the value of Kc, and we'll talk about whether it increases or decreases. Raising temperature results in a shift in equilibrium in the endothermic direction, lowering it in the exothermic. That sometimes is very difficult for the kids to master, so I tell them to put the energy term in and make it work. In most cases, when you are trying to make a solution, you'll find the endothermic technique works. That is to say that if you're trying to dissolve solute in solvent, you'll typically heat it up because solution formation happens to be endothermic. If you consider this reaction shown here, I'm giving you a negative delta H. That tells you that energy is on what side of the equation? The right side, throw it in. In which direction will a net reaction occur if the temperature is decreased?
Forward direction.
Forward direction. to replace the heat lost. But let's think about this now. What is the effect on Kc? The Kc is product concentration over reactant concentration.
So if you treat energy like it's a product, and then see if the
No, because
denominator.
it determines.
No,
what
no,
it
no.
does to
Hang
the
on, hang on.
chemistry.
One thing, hang on. We said as we increase temperature,
Are we decreasing temperature?
all right, let's decrease temperature. If you decrease temperature, equilibrium shifts to the
Right.
right. In shifting to the right, what happens to concentration of product
Increase.
and reactant?
Decrease.
And so what happens to Kc?
Increase.
Increase is correct.
Wait.
This is for an exothermic reaction. Don't memorize, interpret. Although the bottom line is, if temperature alteration results in a forward shift in equilibrium, Kc will increase. If temperature alteration results in a reverse shift in equilibrium, Kc will decrease. If, on the other hand, we increase temperature, equilibrium would shift to the left. And now, if equilibrium shifts to the left, what happens to reactant concentration?
Increase.
And product
Decrease.
and Kc
Decrease.
decrease. And that's how you interpret your Kc change. The only factor that alters the value of Kc is temperature. All right? The question also says, in which direction will a net reaction occur if the pressure is increased? If you increase pressure, equilibrium shifts to the
Left.
If you increase pressure, equilibrium shifts to the right, because the volume of gaseous product, which is 2 mils, is less than the volume of gaseous reactant, which is 3 mils. When you increase pressure, equilibrium shifts to the side with the smaller volume of gas,
Why wouldn't concentration affect Kc?
because it equilibrates out. Last question says, is the conversion of SO2 to SO3 more nearly complete at high or low temperatures? If you want this conversion, do you want a forward or reverse shift? Forward. If you want a forward shift in this exothermic reaction, do you increase or decrease the temperature? You decrease it because the reaction is exothermic. I have 2 tiny little pieces to show you, and then I'm giving you the rest of the period to practice, which you need. The example problem listed here I'm going to give you at the end to make sure you can synthesize everything. I think you'll be very solid there. Catalysts affect reaction rates. However, they don't affect equilibrium. A catalyst, we know, provides an alternative reaction mechanism with a lower activation energy. As a result, the rate of the reaction is increased. However, a catalyst speeds up both the rate of the forward and reverse reactions such that they're increased to the same extent. A catalyst has no effect on chemical equilibrium. The other thing I want to show you, and I don't believe you're going to find this in your textbook, but I have seen it on recent AP exams, it is in your review packet, is as follows. We just want to look at the graphical consideration with Le Chatelier's principle. At the very beginning of the chapter, we looked at how concentration versus time was affected as equilibrium is reached. These are the initial concentrations here. When equilibrium is attained, you get that plateau. What's going to happen here is you're at equilibrium and we're going to stress the system. Let's say we add hydrogen gas. we know if we add hydrogen gas, equilibrium shifts in the forward direction in an effort to use the hydrogen gas we added. Let's look at Le Chatelier's principle graphically. Let's say, for example, that you have decomp of hydrogen iodide to hydrogen and iodine gas. Shown here, you're at equilibrium, and I'm not sure where this came from because I'm a little surprised that this is so much higher than this, but in any event, let's run with it. Here's equilibrium where you're plateauing. At equilibrium, Q and K are equal. We're going to add hydrogen gas. You'll see the addition of it, upward trend there. You're adding it. Its concentration is increasing, and you dump it in very quickly. Now let's look at what happens to re-achieve equilibrium. As you increase hydrogen gas, equilibrium shifts to the left. So these amounts will decrease and this will increase. And look, hydrogen increases, and then when it plateaus, you're at equilibrium. The hydrogen spiked up due to the addition, it decreases, and you're at equilibrium. Note that it's higher than what you started with because you don't utilize everything you added. Note here that the iodine decreases until equilibrium is reestablished.
In this reaction, if you were doing it in the lab, how would you just add hydrogen gas?
Probably syringe it in. So if you had the reaction in some reaction vessel that was capped, you would take a syringe through the rubber stopper and you'd go whoosh. Similarly, we've got nitrogen with hydrogen gas to form ammonia, and we're going to increase concentration of hydrogen here. Equilibrium will shift to the right. These will decrease. This will increase. Take a look. Increasing until the plateau is reached. Decreasing. This was an increase and then a decrease. This little picture right here is exactly what you're going to see, unless they're mean and they pull something out. But when you remove something from a system, it's tricky. When you remove something from a system, typically it's through the addition of another substance. If I wanted to remove hydroxide ion from a system, I would add acid. If I wanted to remove chloride ion from this system, I would react it with some cation that will generate a precipitate. So the removal is tricky, and if you saw this as a multiple choice question on the AP exam, you are going to recognize that straight on because you've seen it, and there's really no way that I can think of that will change it.
Is aluminum the most soluble?
Say it again.
Is aluminum the most soluble, not counting group 1 and group 2 metals? Is it,
You mean,
like, is aluminum chloride more soluble than, it's more soluble than lead chloride or silver chloride?
you're not comparing apples and apples. Your 3 insoluble chlorides are silver chloride, mercury 2 chloride, and lead 2 chloride. Aluminum chloride happens to be soluble. In regard to solubility products, we're going to get there like with the aluminum hydroxide, but that has a pretty tiny KSP if I'm remembering correctly. I think it's like times 10 to the negative 27. Don't quote me, I got to look that up. But I don't think you have an apple-to-apple comparison there, so be careful. Yeah. In any event, Le Chatelier's principle with practice is very easily mastered, especially at your level. Spend the time to master it. It's a gold mine in terms of the AP exam. It's so easy. You will nail every Part 1 question there. If you are fortunate enough to get a Part 2 question on it, jump out of your seat and then quickly do the question successfully. You can't ask for anything better than Le Chatelier's principle. We're going to get into illustrative chemical equilibrium next time. I did a lot today because I want to cover that next time with about 45 minutes of practice next time. I will give you your practice quiz. I'll tell you which questions to hold on until Friday. With that said, all the other questions should be done for Friday. If I were to give you a little mini quiz on this concept, I expect mastery for Friday. I'm going to give you a Le Chatelier's principle question from your textbook to prove to you now that you either have the concept already or you will have the concept by Friday with practice. So I'll put that on the screen and I'll make it bigger and I'll let you give it a shot.
Number 16.
This is actually from a different textbook. I just really like 1616 there, but you have a question.
Will they ever show any of the other, what are they called, like perturbations, graphically, or just concentration?
That's a really good question. I've only seen concentration asked.
Okay.
You typically plot concentration during time. However, you could plot pressure during versus time. So I could see that one, not temperature. But you never know what you're going to see in May. So give 1616 a try. We'll go over the answers, and then hopefully you'll feel confident with Le Chatelier's principle.